Thank you very much, Sandeep, for the introduction, and thank you for this opportunity to talk again about bright scatterers, these new toys, so to say. The backscatter polarimetric signatures from bright targets are ones among several information sources we have at MeteoSwiss. Just like the sun, they are for sure the most cost-benefit wise. Furthermore, they are available day and night. And as we will see in a minute, in some cases, for instance, important hardware replacement, you can use it for monitoring maybe, but it's difficult to use it for calibration, even relative calibration. And this is the propagation path. It's quite ideal for Switzerland, maybe not for other countries. And this is the first requirement to have a bright scatter. You need the scatter to be hit by the beam axis. Here you see in blue the first Fresnel zone. So there are many Fresnel zones that are free. And then you have the mountains at the same altitude of the bright scatterers. You have more or less a mountainous uniform background, and then you have a bright target. In this case, a metallic tower, 90 meters tall. And since the range is 18 kilometers, the resolution in azimuth and in elevation is 100 times Greek pi. And in range, the resolution, we use a pulse width of 500 nanoseconds, so around 75 meters. So it contains the targets. And with this configuration, we get a signal which is of the order of 80 dBz, which means minus 18 dBm, not too far from the saturation point at minus 10 dBm. You have already seen this slide, and it's the statistic of 5 days in January, which from a propagation point of view is probably the best month, and winter obviously is the best season. And you see that the bright target gives a contribution that reinforces the uniform background. So you cannot expect a Rayleigh distribution, and in fact the distance between the linear mean of Z and the median of Z is the ratio is close to 1, no? So it's close to 0 dB, the difference on log scale. And also you can see that for this bright scatter, the standard deviation of reflectivity was relatively small, around 1 dB, both horizontal and vertical polarization. And since the two polarization are relatively typically high correlated for such bright scatter, so the correlation coefficient of the time series in time is larger than 0.5, then also the standard deviation of ZDR is smaller than the minimum of the two. And even more interesting than reflectivities is the standard deviation of other polarimetric signatures, such as CDP, the differential phase delay, for instance, with a standard deviation of 4 degrees in this case, and the standard deviation of rho HV. So rho HV, the average value was relatively large, and a standard deviation, as you can read there, 2.4 milliunits. Having said that, we come to the discontinuity point. The discontinuity point was the change of the calibration unit, new calibration unit, 4 new LNA for the low sensitivity channel and high sensitivity channel. In this case, for such a strong signal, we are using the low sensitivity channel. And this is another advantage of bright scatter, because for weather, typically you use most of the time the high sensitivity channel, and you monitor is more this channel. Low sensitivity channel, you use it for hail close to the radar, basically. So I took the best day. You already saw this in Toulouse. I took the best days in January 2019, and I compare it with the best day in January 2020. And then the results was somehow shocking. We were discussing this with Leonardo, and we came to the conclusion that it was not that easy to explain why. But what I decided to do is to cope with this situation. So to see the evolution. So, okay, I have a different statistic for my bright scatter. We found another bright scatter. This time, the new bright scatter was not found visually, but rather statistically. So we were looking for another beam that had a small standard deviation of rho HV. And we found a mountains amphitheater, so to say, a place that has no bright scatter. So I call it mountainous bright scatter, but it has a very low standard deviation of rho HV and even better performance than Cimetta itself with the old calibration unit. Same as with the new calibration unit. And here you see some seasonal statistic. I took the average over 1 week and the standard deviation over a week, and here you see the differences season after season. Previously, another facts that bothered me was the value here of the reflectivity ZH and ZV after the change of calibration unit, because it was much smaller than the level that we had with the old one. While with this seasonal monitoring, you see that January 2020 was somehow unlucky in the sense that 76.5 mean, 76.5 mean is at the limit, low limit of ZH, and 72 dBz is at the low limit of the ZV for Cimetta. And here there is also the other bright scatter, Montevada, with the two polarization. And you see that also with the new calibration unit, it has better performance. Performance has reduced. The standard deviation got wider, but still the situation remains better. So Montevada is better than Cimetta in a relative terms. Then I went to rho HV, and something similar. Season after season, you see Cimetta has a larger standard deviation, and rho HV and Vada has a relatively smaller standard deviation. And next was the idea of changing the paradigm, so to say. I have seen that I have a new situation regarding the statistics of this bright scatter. And what I thought is that maybe I cannot do the monitoring on a daily basis, but I can perform it. We can perform it on a monthly basis. For instance, by selecting 5 good days per month. And this is what happens in for the last summer, no? So here you have rho HV and you have the standard deviation for each day at the daily level. And so I concluded, yes, maybe I can go on tracking the statistic of this polarimetric signature and tracking these two bright scatterers, Cimetta and Vada, month after month, and see what is going on. Similarly, for CDP, here you see in degrees the backscatter differential phase shift, and actually in this clear sky condition, it's coincident with the backscatter phase shift delta. So what we are seeing is that the standard deviation remains more or less small. And again, Montevada in blue is better than Cimetta, but it has still reasonable results. And then This is for reflectivity. Again, Cimetta and Montevada, and 5 clear sky day per month of the last summer. This for what concerns the new calibration unit of LEMA. At Albis, we were luckier in the sense we still have the old original calibration unit. And the bright scatter, as I shown in Toulouse, has a very small dispersion of ρHV. You see, it's 0.2 milliunit in 2019, 0.1 milliunit in 2021 for 4 consecutive days. And the next slides show you the behavior of ρHV over 1 year for 2022. You see that the standard deviation is really small in this case. So with this LNA of the original calibration unit, a bright scatter like this one, which is at 34 kilometers from the radar, gives a very nice and small dispersion of ρHV. And so far, so good for our rotation antenna. What happens if the antenna is fixed pointing? We had a chance to monitor that thanks to a campaign that was done with an X-band radar near Schaffhausen. And we were illuminating with a stair mode a wind turbine. And the wind turbine, so the antenna is not rotating, but the bright target may rotate in this case. And the rotation could be the blade rotation, so the rotor speed, or could be the blade pitch angle when you have a transition from moderate wind, energy production, and no wind or strong wind. And also you may have a rotation in azimuth of the nacelle. So it's the orientation of the nacelle with respect to the radar. And we had every 2 hours, approximately 100 minutes of observation in stair mode. And I will show you 32 minutes during the first day of the campaign. Probably some of you have seen this slide in Toulouse. Martin Lainer showed it. This is the whole campaign, and you have all the echo, ZH, every 64 milliseconds, because the PRF was 2000 Hertz and we average 138 pulses. And we had information from the wind turbine every 10 minutes. So 600 seconds. And here you see all the echo with the original high temporal resolution, and also a median average every 10 minutes in red. And now I will blow up during the first day, and I will go into quite some detail. As I said, from 1708 to 1740, and there are 4 periods. The first period, I got from the manufacturer the information that rotor speed was 0. So no movement of the blade. Then, and you can see it, the rotor speed here, no, if you focus here. Then the next 10 minutes is not exactly 0. It was 002, sorry, revolution per minute, means in 10 minutes, 0.2 rotation, 72-degree rotation. In period number 4, another partial rotation, but not even one complete term. And in the intermediate period, P3, we had 22.5 rotation. So part of it is an energy production mode. And now I will show you ZH. No, ZV, sorry. And you can see the 4 periods, no? And it's easy. When the rotor speed is 0, ZV is almost constant. In some minutes, it's even constant, because here you see in green, the median every 8 seconds. In blue, you see the in black, you see the median every 8 seconds. In green, you see the maximum every 8 seconds, and in blue, you see the minimum every 8 seconds. So green and blue are the envelope. You have a very fast fluctuation. and the mean is black. And then you can see during P2, there was a period that we could consider also no rotation. And then at the end of the period, probably rotation started, and then the envelope became wider. Similarly, if you go to the end of the point here, you see that for the last 40 seconds, again, probably you had no rotation there. And again, the envelope became quite small. Information from ZH are similar, although different. And here is the slide. And again, you can really conclude that the first part, you have no movement. We are sure that the first 2 minutes we had no movement, but probably this was lasting for a large part of period P2. And then in period P2, a small movement started for the blade. And then it started a rotation period during P3. But we see here 22.5 rotation. Probably maybe say only 2.5 rotation were at the beginning and the end. And then you have maybe 20 rotation in the 4 minutes that are in the central part here. And in this central part, you can clearly see that both the maximum and the minimum stabilized somehow. And probably this is due to the fact that the windmill was rotating faster. And interestingly, we can now blow up a period that I have called during period, a sub-period during period P2, that I've called P2B, where you see this change in ZH and ZV, but no change in ρHV. So thanks to ρHV, I have really concluded that at the beginning of period P2, there were probably no rotation of the windmill. And I now zoom into this time interval, which is approximately 80 seconds. And I show you CDP. CDP, which is again coincident with delta, with the backscatter differential phase shift, because it was a clear sky day. So you see that delta is going from a fluctuation around 0 degree down to up to minus 460 degree in relatively short time. So the backscatter differential phase shift changed a lot. And I think that the reason could be either the change in the blade pitch angle or a change in the rotation of the nacelle, or both, because this is something that has changed. Well, if you look at ρHV, you think that you would conclude that there was no movement, no rotor speed movement. And after having said that, I can show again ZH. You have already seen it, and now I will show it to you at the full high resolution. So 1 point every 64 milliseconds. And now that we have discussed it a bit in detail, I think you can really identify all the phases. A first period with no rotor speed, then a changes, and then a transition into an energy production mode here. Sorry. A transition into the energy production mode here, where you can clearly see that probably the rotor was going faster. And then small movement that has caused the peak, the maximum peak we have measured during the campaign here. I'm sorry, it's so sensitive, this mouse. I apologize for this. Here you see 2 peaks at 78.5 dBz, which were actually consecutive. So overall, we have 4 values at 78.5, which is the maximum of the campaigns. So probably while the rotor was moving relatively slow, we could reach this extreme positive interference that caused this maximum. Well, you can see that the minimum went down up to 24 dBz. So a negative interference. And finally, we have ZDR. Again, now the plot is every 8 seconds. And to conclude, I will show you now what I've called the subperiod P2A of the wind turbine, where I will show CDP and ZDR. And this is again quite surprising, because for an X-band radar, it is well known that CDP and ZDR are related in precipitation. But it's quite surprising to see that even an object like the wind turbine, for a short period of time, here is just 8 seconds, but it was like this for about 20 seconds, you can clearly see that ZDR and delta are related, so that the correlation between the two is very high. And you can see that the peak and the valley of the fluctuation are synchronous somehow. And so something is happening to give this coherent fluctuation every 1.7 seconds. So really a wind turbine that look like precipitation somehow. And with this I conclude. So a still wind turbine can connect like a bright scatter. And of course, thanks to the fact that we had this campaign, we could prove that part of the dispersion of part of the fluctuation of the polarimetric signature are due, as expected, by the fact that the antenna is rotating. If the antenna is not rotating, you can get even smaller dispersion. And the other things that I have learned, that even if you change some hardware, that will change a bit the statistic of your scatterers, you can still do something about it. Maybe you just adjust the time of monitoring. In this case, for LEMA, I went to monthly monitoring instead of daily monitoring. And the final question, this is also for Leonardo in the room, and we will see it. What is going to happen? What is going to happen when we change the calibration of unit of Albis? Will the properties of the Albis bright scatter change, or will they remain more or less similar? And we will see this in the future. Thank you very much.
Statistical technique for detecting these bright scattering spectra. I was wondering, have you run that across the network to get a feel for how prevalent these targets are at a typical site?
Not yet, actually. Really, what I did is I tried to find a bright scatter either visually, because I know the place, or statistically by looking at these small variables that they are. And so far we have identified overall 8 or 9. And what I'm trying to do is to have at least one bright scatter per radar. But it's still something going on. It's somehow time consuming, yes. I did all these mostly in spare time.
To replicate this method of the bright scatter estimation, I think we have 3 radars which are quite close to big mountains, around 40 kilometers, 60 kilometers. We look at data from only PR days, right? No weather conditions.
Start with clear sky day, yes, and then see how this dispersion of ρHV changes. Frankly speaking, I was surprised to find Montevada. Marco Boscacci gave me the statistic over 1 year of all possible points with very small standard deviation of rho HV, independently of the weather. And then Montevada was this point. And then I said, wow, it's even better than Lema. And then because it's really a wild mountain in a wild national park, it's Parco Nazionale della Val Grande. So, and also if you go there, I was really surprised. This is a mountainous backscatter. There's not a bright target, but probably is the way the amphitheater backscatter the signal toward Lema. That yes, the best thing is, and your question is strictly linked with Teams one. You can try some statistical method and look at the standard deviation of rho HV. If you think you have. But if you have a bright target that is hit, that is along, this is even better. I would start from that. You can go with both approaches, I would say. Yeah.
So if there are differences between summer and winter, so the snow conditions affect maybe the...
Yeah, propagation in summer is definitely much worse, because if you think of refractivity, that depends on the partial pressure of water vapor. Then in summer, you have a higher temperature, so the amount of water vapor double every 10 degrees. So yes, propagation is affected quite a lot by, and in fact, I get worse, on average, I get worse results in summer than winter, on average. There are many things that I still have not understood, many, but one interesting thing is that weather is not that important. So typically, and this is why a bright scatter is so interesting also from a meteorological point of view, to evaluate attenuation, path integrated attenuation two-way. Because really, I have, I don't know, 80 dBz plus minus 1 dBz. And when I have hail or melting hail between the radar and the bright scatter, I have drops. I have seen drops of 20, 30, even 40 dB. And I've seen drop, they just last 5 minutes, but even 30 dB with the vertical polarization. And then this is very promising, because Guy Derieux is using mountainous scatter, but doing an average over a large areas. While with this approach, you can have information of one azimuth, 1 or 2 azimuth. I didn't say that, because you can see the bright scatter in 2 azimuth or even 3. It depends. And they are very correlated, the 3 value, because of course the gain of the antenna is not able to. So you see the bright scatter at various azimuth. And so I think this is also very promising to use it for path integrated attenuation and have an idea of alpha in your relation of attenuation. Yes.